How much? Hey, how much is $1? How much is $1? How much is $1? Probably like 2 cents. How much is $1? Probably 2 cents. Are you being serious? Oye, funny, one of those too. It's like nothing. 100 is like $45. Okay. ¿Cuánto? $0.41. 41 cents. No, wait, that was 41 cents. Oh, yeah, but it's kind of like the same though. Because 10 minutes and then 20 is like close to $1. It's like, Eddie, can I use Eddie? Yeah. Yeah. 200. Qué loco.
I've been paying attention. You, bro.
Good morning, ladies and gentlemen. How are we doing today? What? Okay, here's the thing. I'm going to put out 2 charging blocks from now on. The first 2 people who get them, and the rest of you need to charge your computers and bring them charged. Because this is kind of getting ridiculous. Eric, what percent is your computer at?
15.
15. How long is that going to last you?
Not a long time.
How long does it say, Eric?
It says 2 minutes.
Eric, if it's wrong, I'm taking that charging block away from you.
No. It says 2 minutes and 10 seconds until full. That's what it says. 2 hours. Or 2 hours.
2 hours and 10 minutes. 15%. Calculating.
But it won't last that long, actually.
2 hours and 3 minutes.
Okay, let's see if it actually lasts long.
Okay, let's see. How long? What's your percentage?
It'll probably be dead. Yeah, it's
Dead. That's a bad percentage. Come on, guys. Your responsibility is to bring a charged computer to school. You're not going to tell me it died in the first hour.
It did.
Yeah, because you didn't bring it charged. So, come on. I expect this from freshmen. I don't expect this from you guys. Let's get it taken care of. Oh, lefty ladies and gentlemen. Today, open up your computers. I'm going to send you a Pear Deck, ladies and gentlemen, for review. You may need a piece of paper to do some scratch work on. That's up to you. Here we go. Just sent it to you, ladies and gentlemen. All right. Shenza. Good. Pierce. He's alive. Jack. Hey, Skylar. No, Ben. Ariana. Jasmine. Yes. Steven. Yes. Irving. Yes. Phoebe. Yes. No. Christopher. Yay. I mean. All right, question number 1, ladies and gentlemen. Convert 52.3 Kelvin or Celsius into Kelvin. Is it dead yet, Eric?
No.
Okay, good.
Wait, what is this?
I forgot. Celsius.
You know, it's a good thing I'm not expecting you to remember them. I'm expecting you to write them down and put them on your periodic table so that you can use them on your test. Because I will not be giving this to you on your test. Oh, and by the way, you got a quiz tomorrow, ladies and gentlemen.
What?
Friday.
What?
Wait, what day is
What?
I said Friday.
No. Did it?
Yeah.
Sorry, tomorrow. We can't do it on Friday. It'll interfere with our lab. So. Pierce, what do you got?
Oh, shoot.
I'm sorry, one more time? 325.3? What the heck? Whoa. Hey, wrong button. Wrong button. Hold on. Hold on. You don't want to see those people.
Those are children.
No, they're random people that I have pictures of. Thank you for asking, though. What, did I have random pictures of people who I don't know? I know it is. Dang it, I just shut everything down, too. Son of a gun.
Wait.
What part of the sentence do you not understand? Sorry, ladies and gentlemen. Technical difficulties. Wednesday. Boom.
No, because they don't actually close.
Oh, they moved this.
So what was your answer again, Pierce? 325.3. There you go, ladies and gentlemen. Good. Now, the Pear Deck died because I accidentally shut it down. So, close it out. Convert 246 Kelvin to Celsius. Let's go, ladies and gentlemen. All right, Eric, what do we got?
Wait.
Wait.
Hold on. Wait. Is it negative 27 Celsius?
What?
Is it negative 27 Celsius? Angel, what did you get? Why?
Also figuring it out.
What?
Also figuring it out.
Okay, negative 27 degrees Celsius. Hope you're quicker on your quiz on tomorrow. Okay? Convert 2.13 atmospheres to millimeters of mercury. By the way, these might be helpful, ladies and gentlemen.
Oh, you're right. Yeah. 1 point to go in.
Oh, no, you can't do it. No, you do it. Minus 360.
Does it say 8 p.m.? It should.
What's the rating? No, but it's 360.
All right. I'm gonna convert this. Yes, right.
Just like the third, right?
All right, Steven, what'd you get?
1,618.8.
1,618.8. That's a lot of digits for 3 sig figs.
Okay. Oh, right. My bad. 1,620.
1,620. Okay, Irving, what'd you get? Okay, Shenza, what'd you get?
Two.
1,620 millimeters of mercury. Good, ladies and gentlemen. Good. Convert 87.5 kPa to PSI. Shenza, what'd you get for this one?
12.7.
12.7. Jack, what'd you get for this one? 12.7. Phoebe, what'd you get for this one?
12.7.
It's amazing. Good job. You all got the right answer. Questions, ladies and gentlemen?
Woohoo!
Okay, that's what's going to be on your quiz tomorrow, along with other things.
What?
Like knowing what the different factors, units, and variables are that affect the gas. Being able to do these conversions and being able to convert from Kelvin to Celsius, Celsius to Kelvin. Questions?
No.
Good, wonderful, excellent, ladies and gentlemen. So yesterday we left you, ladies and gentlemen, with this table on page 22 in your EISN. So here are your answers for what you should have gotten, ladies and gentlemen. If there are any questions, I will be more than happy to answer them for you. Otherwise, take a look at this and tell me if that is what you got. Well, don't tell me. Hopefully that's what you got.
Yeah, that's what I got.
Good! Excellent. Amazing. Incredible. All of the above. Questions, ladies and gentlemen? Okay, you need to get so that you are sitting next to somebody. Go.
Eddie,
Go. Jack, you can slide your desk over either way because obviously we've got an odd number. Okay, so you could be in a group of 3. Okay, so you can either slide over with Faith and Skylar, or you can slide over with Pierce and Irving. Angel, get with somebody.
You're
Get with somebody. David, go by Michaela, please. Okay, all right. Here we go, ladies and gentlemen. One of you is going to come up and grab one of these. May look like this. One of these and one of these. The other one on your computer is going to locate a program called graphical analysis and start bringing it up. Let's go. Let's go. Let's go. Let's go.
Wait, so one of these?
Good.
One of these?
Good.
Oh, I know this.
And then one of these.
Good.
Oh my God.
Paid attention. Wonderful. Wonderful. Here's the good news, Jack. Yep. Come on in, Christopher. Go sit by Jack.
Bro, es que he...
Bye bye.
No, sí, no, sí.
These?
No, one of these this.
Okay.
You need one of those. There you go.
Yep, and good. You got everything. Okay. Good. Sit down, sit down, sit down. Okay? Now, somebody in your group should have brought up graphical analysis, the one who didn't come and get the stuff. Yes. Do you know how to find it?
No.
Okay. Go to the little circle in the lower right-hand corner. Click on it. So if you go down to the bottom, go to the circle in the corner, and it will bring up all of your apps, and you are looking for one that has a white circle with a red and a blue graph line on it. And that is what you will select. Mine looks slightly different, ladies and gentlemen, but this is what mine looks like. Yours looks like that, basically. The red and blue graphing line, and it says, yours says, I believe, Vernier Graphical Analysis as well. So click on that and open that up, ladies and gentlemen. Now quit playing with the syringes and get ready to go. We are going to start looking at our first gas law today, ladies and gentlemen. And our first gas law is called Boyle's Law. Boyle's Law involves 2 of the 4 variables that affect the gas. Okay? So, what are the 4 variables that affect the gas? Give me one of them.
Amount of gas.
N, amount of gas. T, temperature. What else? Volume and pressure. Looking at the equipment you have, tell me which 2 variables are affected by Boyle's Law. Pressure. Why pressure? Joshua.
It says pressure.
It says it's a pressure gauge. Good. Always go with reading the instruments. Actually, that's what I was absolutely hoping you would do. Okay, so what's the other one, ladies and gentlemen? Nope. Nope. Doesn't. No. Nice. Good. What? Volume. Those are the 2 factors that we are going to be working with today, ladies and gentlemen. Now, you are correct. You could change the amount of gas in the syringe, Phoebe. For most of these gas laws at the start, though, amount of gas is the thing that is normally held constant because you put the gas in some sort of container. Okay? Was a good guess, but not for what we're doing here. Okay, so here's how this works, ladies and gentlemen. This part here, the one that says east on some of them, this gets plugged into a USB port on the computer that is running graphical analysis. So plug it into the USB port on your computer that is running graphical analysis. This pressure gauge then gets plugged into the end of this. This lets the pressure gauge talk to your computer. Try not to drop things. There's only one way to put those 2 together. Because of the tab on there, there's only one way it can go in. Okay? Hold on, Steven. Okay? Now, on this, it should be showing pressure and time because it should automatically detect what sensor you are using. I don't really care about the graph, though. So up here, this box where you have the 3 squares or 3 rectangles inside a square, click on it, unclick graph, and click meter, because that is what we are using it for. We're using it for a pressure meter. Okay? Now, the other one of you who does not have your computer on graphical analysis, you need to go into Google Classroom. And in Google Classroom, ladies and gentlemen, there is a Boyle's Law activity that I want you to open up. Okay? So open that up, ladies and gentlemen, and it looks something like this. Okay? I'm going to open up mine because I need mine up so I don't ruin yours for you. Okay? So, in a minute, ladies and gentlemen, we are going to use the pressure gauge in the graphical analysis to read the pressure that is going to be created when we change the volumes inside your syringe. Now, what is inside the syringe? Air. Okay? So again, ladies and gentlemen, to use this syringe, you're going to pull it out to where it is reading 60. Now, there are two lines that you can see very clearly up against the plastic casing of the syringe. The bottom line, the one closest to the cone, is the one that I want you to set at 60 right now. It cannot be hooked up to anything. It needs to be at 60 right now. Is there anyone who needs help or has any questions? So the two lines that you can see, okay, you've got three lines. The one that is closest to the cone, to the end of the syringe, is the one you're going to use to measure with.
So you want to use that top one closest to the cone shape. Okay?
All right? Everybody else good? Okay. So, here's what happens, ladies and gentlemen. This will screw into the end of this. So you take and you put it together, and then you turn it clockwise to screw it in. Now, you need to be careful, because if you take and put too much pressure on this, you will break this right there. And I cannot get a replacement for that. So you need to be careful now, okay? As long as you don't drop it or try to bend it, you will be fine, okay? So now you should have everything hooked up. Now, ladies and gentlemen, if you look, you should be reading a pressure on the graphical analysis software. Questions? Okay, so here is what is going to happen, ladies and gentlemen. You are going to fill out this table by changing the volume in your syringe to 55, then 50, then 45, then 40, then 35. Now, just wait. So what you do is one person is going to squeeze the syringe to get to the new volume. The other person is looking at the software, at the number. And when you get to the volume and the person says, okay, you are going to write down the number that it is closest to on there. Now, that number may move around a little bit. So hopefully the person will hold it steady. And when they do, they can go, all right, I'm at the volume. You record the pressure. And you're going to take that pressure and you are going to put it into here. Okay? When you're done with one, you go to the next one. All the way down until you get to 20. So, right now, you need to collect these pieces of data, please. By the way, one last thing, sorry. When you are pressing on this, hold this part in one hand and push the syringe in with the other. Don't hold up here and push in. You will break that connection. Hold the syringe in one hand, push in the plunger with the other until you get to the desired volume you are trying to measure. Okay? Whatever line you set at 60, that's the line you are always using from here on out. So whatever line you put at 60, use that to get to 55, use that to get to 50, so on and so forth. Jack? Okay. Yep, you're right. Once you plug that in, Jack, it should be fine.
Not yet.
Well, it's really still 134.86. 81.
Oh, I know, what was he saying? Sorry.
You're shaking the light. So you're shaking.
I can really see shaking. You're shaking. I can see you shaking.
Okay.
Jasmine, you okay?
No,
What's the matter?
I don't have arm strength.
You may have to sit.
It really is.
I'm trying to push it.
It's not reading it anymore? Write down what you get.
Just push it.
Go. It's going to
97. I'm not doing anything.
Is there anyone who needs more time?
Yes.
Okay, I think that's gonna.
25.
Is it gonna pop?
If you
It's what kind of power?
like push it all the way, I feel like it's too much.
To all the way to what?
Like 10 or 5?
Oh, I wouldn't do that. I wouldn't do that. There's a reason that we're stopping at 20. What's that? Well, here's the problem. If you unscrew it after you have started, now we have a chance of changing another variable. What variable? Nope. Nope.
Oh, it's not moving. Yeah, it's the same thing.
Once we attached it, what variable could no longer be changed? The amount of gas. So the reason we set it for a number and then attached it, we are no longer able to change the amount of gas because we are now a sealed container, a sealed system all the way to the detector, to the meter. And that is what we wanted. We only want two variables changing here. Okay? Keep that in mind. Okay. Are we done?
Yes.
Okay. Here's what I want you to do. You don't need to record anything. I want the person who was not pushing on the syringe to now take the syringe and just push it to see what it feels like when you try to get to 30. Well, let's do 40, then 30, then 20. So if you didn't get a chance to do this, try to go down to 40, then try to go down to 30, then try to go down to 20 or 25. Oh.
Why is this so easy?
Got it.
Oh my god, I see what I'm doing.
Now,
Wait, you know do this theory?
Yeah.
Oh.
Yeah, it caps at 230.78.
Okay, once both of you have done that, unhook your device, unhook the syringe from the meter, and then bring everything back up and put it back where you got it from, please.
Did yours stop at 230.78?
230.18. 232.18.
Yep.
That's not reading it.
Oh, I need the thing here.
And yep.
Yes.
Oh, where's that at the top? Where? Why? This is the
Oh, yes, it was. Oh, you didn't work. Oh, because I was she called me last week. There's a guy, there's an actual guy that he's a his name is Leon Laffer. I have a picture of him. He's like, it's just that his name is Steven, and it's with the I. It's this.
Thank you.
Give me $10.
Actually, oh yeah, I'll pay you.
Bro, did you
Can you actually cut hair?
Some of them didn't have cases.
Oh, okay.
Some of them did not. That's fine. All right, everybody got everything back? Okay. Now, there's a reason that I asked the other person at the end to push on the syringe. Why? Okay. So you tell me what's going on here. What's the interaction between pressure and volume? Well, let's think about this. Which one did we control? Which variable did we control in this lab, ladies and gentlemen? We control pressure? Really? Because we pushed it to what? To a certain volume. Which one did we control? Now, the independent variable in this lab would be volume. You decide, well, I decided for you, but we had to get to 55, 50, 45. That is what we were controlling, correct? Okay? So in this lab, the independent variable was the volume. Okay? And what were we doing to the volume? We were making it less. It was going down, correct? What was the dependent variable? The pressure. What was happening to the pressure as the volume went down? How do we know? Other than looking at the gauge, how do we know for sure that the pressure is increasing as the volume gets smaller? Because it's physically harder to push to those smaller volumes. And that is what I wanted each of you to experience. Okay? We were controlling the volume. We were trying to get down to 40, down to 30, down to 20, whatever it was. And because of that, as we were trying to get to a smaller and smaller volume, as we were compressing that gas, it became harder and harder to do. And you could physically feel that. So we know now what kind of relationship is this. This is an inverse relationship. This is an inverse relationship. Okay, good. Okay, meaning that as the volume goes down, the pressure goes up. If volume would have went up, pressure would have gone down. Again, opposite directions. Okay. How do we know temperature didn't change? We didn't take and put it into hot water bath. We didn't take and put it into a cold water bath. We left it what temp? Room temp. How do we know the amount of gas didn't change? Okay, but also because of what? You're right, we didn't change it. And how do we know we didn't change it? Because it's a sealed system. If these gaskets on here are good, nothing should leak out. If the connection between these two things is good, again, nothing should leak out. We have established how much air, the number of particles inside of there, and then we didn't change it. So again, we are just changing two variables. And for this lab, our variables are pressure and volume. Our variables are in an inverse relationship. Now, let's talk about what a bunch of you found. What did you find as you were going down to lower and lower volumes? Okay, look at the last two. They're the same. Okay, so this is my data from earlier today. Don't expect yours to be the exact same. Don't expect yours to be the exact same. Okay, but if I look at these two numbers here, are you telling me that it was as easy to go to 25 as it was to go to 20? So what is that telling us about these numbers, ladies and gentlemen? What has happened? Why are they the same? Because I thought it was harder to get down to 20 than it was to 25. How come the number doesn't change? Do you think it should have? What should it have done? It should have what? It should have increased. Why didn't it?
There's a limit on the device.
This device has a limit as to how high a pressure it can read. You want to get it down to 10, you want to get it down to 5, that's fine, but this device can't handle that. It cannot go to that high a pressure. Most instruments have a range in which they work. This one, the top is around what? Around 230, 231, 232. So maybe you got 231, you got 232, somewhere in there, but we're all in that same basic boat, right? So what do we know about the last point for sure? What do we know about that last volume at 20? So is this a good point?
Yeah.
You think so? You think when we went from 25 down to 20, this should not have changed?
It should change.
Then is this a good point? What I mean is, do you think this is the accurate number? Do you think this is what we were supposed to get? So should we use it? No, delete it. Delete this whole line. Why? I know that point isn't any good. There's no way going from 25 down to 20 that the pressure should not have gone up. That line can get deleted. Okay? Now, the question is this a good point here? Well, let's look into that just a little bit before we decide yes or no. Well, here's what I mean. We're going to take a look. What happened when I went from 55 to 50? How much did it go up? About. Just give me a round number. Don't give me a decimal. About how much? About 11. All right. From 55 to 45, it went up how much? 13. From 45 to 40, it went up about how much? Okay. So first of all, are these changes the same each time? We're going down by 5, correct? That's the same. Volume is decreasing by 5. That's the same. Is pressure changing by the same amount each time? It's actually what? It's actually getting bigger. And that's fine. But we understand that now, right? Okay. So let's quickly take a look at the next 2 points. How much? 22. The next 2 points. How much? 25. The next 2 points. 35. Okay. Does this seem kind of reasonable?
Yeah.
I would agree. What I was worried about is what if we were going up 11, 13, 16, 22, 25, and then this last one was 25 again. Then it probably wouldn't be reasonable. And that's where we have to be careful. We have reached the limit of this instrument, and that happens. But I want to double check, and I want to make sure that this number, if I'm going to include this number, I want to have some confidence that it is an accurate number. And again, I don't know if it was supposed to go up 35 or not, but I do know it went up more than this one, just like every other one had, correct? So at least that does give me some confidence that this is a good number. Okay? This is a good number. All right? So we're going to leave that and we're going to use it. Okay? Now, if you look at your numbers, and you've got to look at yours, and this last change is not greater than the change before it, should you use that number? No, don't use it. It's got to at least be bigger than the one before. Every one of these gets bigger. So it's got to at least get bigger as well. Okay? Questions? All right. Now you got a couple tabs on the bottom of your screen here, ladies and gentlemen. Go to V versus P tab. Oops. Sorry, I got to get out of this for a second. Okay? Now, when you look at this, ladies and gentlemen, it's just a bunch of dots, right? Imagine it being a line, though. First of all, what do we notice about that line? Huh? Are you on P versus V? Or V versus P and not V versus 1 over P?
Yeah, just P. Yeah.
This tab?
It might be increasing.
Okay, let me check. Maybe I have something set up wrong for you. Hold on. Hold on.
I need to skip it.
Okay, sorry. I have them labeled wrong. What do we know is happening to volume in this lab? What do we know is happening to pressure? So what kind of line are we expecting? Well, what kind of relationship is that? Inverse. Inverse. And in a graph of an inverse relationship, which way does the graph go? Down. Sorry, my bad. I have this flipped for you. Please go to the one that says V versus inverse P. Sorry, I will have to correct it for next year or for the third try. Okay? Yours should look like this. And now, which way is that line going? I'm sorry about that, ladies and gentlemen. Down. Which means inverse relationship, correct? Okay. Inverse relationship going down. Okay? Does it look like a straight line?
No.
Again, I can only show you my data, ladies and gentlemen. That point I'm not counting. Does that look straight?
No.
It does kind of do what at the very end there? Seems like. Kind of like flattens out a little bit. Okay? Not the greatest, but we could pretty much see that it's not perfectly straight. Fair enough? Okay. Well, we hate inverse lines in science. And we hate lines that are not straight. So we're going to do a little trick here to try to make this into a straighter line. To do that, ladies and gentlemen, in your data table, I have this for you. Okay? I have volume, I have pressure, and then I have 1 over the pressure. Okay? 1 over the pressure. Okay? So, these numbers are doing what? What are these numbers doing? They're decreasing as well. They are decreasing as well. Which means what kind of relationship now? Now we have a direct relationship. Now that line that you were looking at in that P versus V, which was supposed to be this one, now we have these. Okay? I'm going to take out that one point that I know is terrible, ladies and gentlemen, because it's messing up our graphs up. Now, when you look at those, what do those look like? Increasing. You tell me.
It's
Pretty straight.
Fairly straight. Fairly straight. Okay? Now, you do not have to do this, but please watch. I'm going to take, and I am going to multiply pressure times volume for all of my numbers here. So when I do that, ladies and gentlemen, I'm going to write a little formula here. Equals, parenthesis, that times that. Close the parenthesis, hit equals. All right. Now, what do you notice about those numbers? And I will make them bigger for you. We will get them all to the same decimal place for you. What do you notice about those numbers? They are doing what? Okay, they are decreasing. Sorry. V times 1 divided by P. I'm going to write another little formula here. Equals V times 1 divided by P. Actually, sorry, I can just use this number here. My bad. I can just use this number here because this is 1 divided by P. You don't need all those decimals. Let's make it a little bit bigger. Okay? All right. So what's happening to our numbers still? Decreasing. Okay? They're still decreasing. But when we look at this line, ladies and gentlemen, if this is a straight line, what does that mean? What's constant? Good. Thank you. The what? Okay, I just want one word. One word. What is constant? Starts with an S, ends with a lope.
Slope.
The slope. The slope is not changing. I can put in a trend line here. Boom. There's the trend line. That is the best straight line through those numbers. Let's try to do that here, ladies and gentlemen. Let's try to put a trend line in. Doesn't really go through many of them, does it? Here, it does. Through almost all of them. Hey, let's do something else here. Customize, series. We're going to add an equation. Okay. So, this is our equation right here, ladies and gentlemen. Get rid of this. 1.59 times 10 to the negative fourth x plus 2.87 times 10 to the negative fourth. What is that line actually? How should we write it? What does it represent? What formula? Y equals mx plus b, correct? Okay, what's y? In this particular graph, what is y? What's on the y-axis?
25.
Nope, what variable? Sorry.
Oh.
Yeah, you're giving me the right numbers. I want the variable. What is y representing? Pressure. Okay? Actually, sorry, 1 over the pressure. That's what this one is the graph of. Sorry. 1 over the pressure is equal to m, the slope. What is x? Plus. Now this number, ladies and gentlemen, is 0.000287. Right? 10 to the negative fourth would be sliding the decimal 4 places. What is this number very close to? It's almost 0. Why would that number be 0, ladies and gentlemen? What pressure would the volume of the gas exert if the volume was 0? What pressure would the gas exert if its volume was 0? None! In other words, that number is close to the, starts with O, ends with origin, which is 0, 0, which is what it should be. Because the only way a gas can have no volume is if it has no pressure. Right? 0, 0. Okay? This is our formula. So I'm just going to put 0 in there. Is that okay? Plus 0. Could we do that? Okay? All right. So I want to solve this equation. I want to solve this equation, ladies and gentlemen. So, let's see. Okay, so we're going to do a little bit of math to this, ladies and gentlemen. Hang with me here. Okay, so I want to get this so that all my variables on one side and everything else is on the other. Okay, I want to get it so that all the variables are on one side and everything else is on the other. Okay, so let's see.
287 it was originally, 284, correct? I need to put that back in there because otherwise it's going to be plus 0 and I don't want that. So I want to take and get this instead of 1 over P, I want to get it to P. So I'm going to take both sides and multiply them times P. Okay, so that is 1 is equal to 1.59 times 10 to the negative 4th V times P. Ah, the heck with it. We'll go back to 0 for this. Plus 0. Correct? Right? Do you understand what I did mathematically there? Okay. So now how do I get V alone? Divide by. So P times V plus 0. I'm going to stop writing plus 0. Why? Pointless. Thank you. Pointless. Is equal to 1 divided by 1.59 times 10 to the negative 4th. Somebody do this on your calculator. Take 1 divided by 1.59 times 10 to the 4th. What do we get?
Is it supposed to be a big number?
Yes, because you're dividing by a very, very small number, which makes it a big number.
62893.0.
We'll stop there.
Yeah.
6289.3. Now, this number, ladies and gentlemen, because this number doesn't change, what does that mean for this number? This number should never change. That, ladies and gentlemen, is called K. K is a constant. In other words, we could predict any pressure and any volume of this gas that we wanted to because we now know what the constant is. We now know what pressure times volume always equals for this gas. And as long as I don't take it out of this setup, as long as I don't change the amount of gas in there, and as long as I don't change the temperature, that constant will always hold for this setup. Always. That means if I want to predict what the pressure would be at a volume of 120 milliliters, I can. I can. Okay? So all this work just to show you what I'm about to tell you. Okay? And that is this, ladies and gentlemen. Boyle's law says that a gas, the pressure of a gas will vary inversely proportionally to its volume at a constant temperature. Now, they don't mention amount of gas, but in these gas laws, we assume that they are held constant. So what that means, ladies and gentlemen, is that if you decrease the volume, what will happen to the pressure? It goes up. If you increase the volume, the pressure will go down. But they will do so proportionally. Meaning, we can use that to make a prediction, ladies and gentlemen. P and V are in an inverse relationship. T and N are held constant. T being temperature, N being amount of gas. Get used to seeing those, ladies and gentlemen. For the next 2.5 weeks, that's what we're going to be talking about. P's and V's and T's and N's. So our formula is P times V equals K. K is a constant. A number that does not change. P is pressure, V is volume. What that means, ladies and gentlemen, is I take pressure times volume. One set of pressure times one set of volume for a gas. I should be able to predict a new pressure and a new volume. Because this constant should be equal to the constant here, which makes these equal to each other. That's what a constant is. Some number that doesn't change. This is Boyle's law, ladies and gentlemen. This is Boyle's law. Okay? That is Boyle's law. All right, we don't need to do that because we already did. Questions? Okay, now what is not involved in here?
Go ahead and tell me what's not involved in here of the four. T and N. So you will have no reason to convert temperature into Kelvin. It's not part of our formula. We only need to do that when it's part of our formula. All right, go to the next page, ladies and gentlemen. So here's a question. A sample of a helium gas in a balloon has a pressure of 240 kPa in a 1.4 liter container. What will be the new pressure if the gas sample is transferred to a 3 liter container, assuming there is no temperature change? What is happening to our volume here? Going up. What's going to happen to our pressure? Go down. Before you ever begin these calculations, you should be able to have an idea of what your final answer will be. My final answer is going to be less than what? Less than 240 kPa. How do we know? Because our pressure's got to go down if our volume goes up. So now we're going to set up our problem, ladies and gentlemen. P1 times V1 equals P2 times V2. I don't have the multiplication sign in there. I hope that doesn't throw you. I'm now going to plug in my numbers. 240 kPa, 1.4 liters. By the way, these two numbers go together, right? Here's the pressure at this volume. I don't care if you want to call this P1 and V1 or if you want to call it P2 and V2. It doesn't matter which one you call it. But these two conditions go together, so they go on one side of the equation. On the other side goes our new volume, 3 liters. We did not get a new pressure. What unit does our pressure have to be in, though? That's not a unit. kPa. Whatever unit of pressure you're in, that's the unit that'll come out on the other side. Whatever unit of volume you are in, that's got to be the same on the other side as well. Okay? So both of these have to be in liters. Both of these have to be in kPa. You want to pick a different unit? I don't care. We can do different units. But the units need to be the same on both sides to do this calculation. So now, ladies and gentlemen, we are going to take and divide both sides by what? How do I get this alone? Isolate your variable. How do I get this variable alone? That's what I'm asking you. How do I solve it? How do I get P2 alone on that side? No! Divided by the volume. Divided by the 3.0. What I do to one side, I do to the other. So 240 times 1.4 divided by 3 gives you a pressure of 110 kPa. Gives you a pressure of 110 kPa. Questions? How many sig figs?
Two.
Well, good. You're giving me a bunch of different numbers. How about we settle on one? How many sig figs in 240? How many sig figs in 1.4? How many sig figs in 3.0? How many sig figs in 110? There you go. There's your answer, ladies and gentlemen. There's your answer. The volume of a gas at 99.0 kPa is 300.0 milliliters. If the pressure is increased to 188 kPa, what will be the new volume, assuming no change in temperature? Quick, how many sig figs in our final answer?
3.
Why, Maddie? Why 3?
Because there's 3 sig figs in kPa.
Correct. The milliliters has how many?
4.
4, but we always go with the smaller amount. 3, 4, 3. We're going to be in 3. Good. Take and put it into our formula again. Okay? So, this pressure and this volume go together on one side. This is the new pressure that is on the other. What's happening to our pressure, ladies and gentlemen? It's going away how? Up or down? Up. What's going to happen to volume? Volume's got to decrease. The only way pressure goes up is if volume decreases. So for this one, ladies and gentlemen, what do we divide both sides by?
188.
188. We're going to isolate this variable by dividing both sides by 188. We are left with 158 milliliters. Our volume went down. What's the argument, gentlemen?
Because I got 112.
Yes, you probably did get 112, but when you round that to 2 sig figs, that 2 has to become a 0, and it's 110 because of 2 sig figs. I would rather you ask those questions than wonder why he just went to 110. Questions? Air trapped in a cylinder fitted in a piston occupies 145.7 milliliters at 108 or 1.08 atmospheres of pressure. What is the new volume of the air when the pressure is increased to 1.43 atmospheres by applying force to the piston? Okay, what is our pressure doing? Increasing. So what's our volume going to do? Volume is going to decrease. So again, Boyle's law, P1 times V1 equals P2 times V2. What's P1? 1.08. What's V1? 145.7. P2, 1.43 atmospheres. What are we dividing both sides by? 1.43. When we're done, ladies and gentlemen, sorry. That is supposed to be 1.10 times 10 to the second. For some reason, I lost my formatting on that 2. That 2 is supposed to be a power there, ladies and gentlemen. This 2 is supposed to be a power. Where did I get 110? Now, there's another way I could have written this. What could I have written it as, too? Sorry, ladies and gentlemen, if this is confusing you. This is supposed to be, this number here, supposed to be 1.10 times 10 to the second milliliters, which is also this. We could write it that way as well.
Okay, so
110. But I need the 0 to be significant, correct?
Yes.
So that's why I either have to put it in scientific notation or put the decimal after it. Questions? Don't lose the packet, ladies and gentlemen. We're going to be using it a lot over the next few days, including when we come back after break. You can return to your regular seats if you wish, ladies and gentlemen. There's only 2 there? Good. You take the bad one and this guy with the good one. Or did you do the other? Okay, good. That's nice of you. It's very nice of you. Okay. Question number 1, ladies and gentlemen. A gas has a volume of 269 milliliters when under a pressure of 105 kPa. Assuming the temperature remains constant, calculate the volume of the gas when the pressure is 145 kPa. P1 V1 equals P2 V2. What's P1? 105 kPa. What's V1? 269 milliliters. What's P2? 145 kPa. What's V2? what we're solving for. What unit is it going to end up in? What unit is volume going to end up in? Milliliters. How many sig figs is this answer going to have? 3. We take this side, we divide it by 145 kPa. What we do to one side, we do to the other. So our V2, what's it equal? First of all, we should have predicted it. Pressure is doing what here? Up or down?
Up.
So what's volume got to do?
Decrease.
So we better end up with a number less than 269. Probably somewhere around 180. Anybody? Anybody? Bueller? Bueller? What do we get? Okay. Again, I was just estimating. 195? 195 milliliters. Okay? Questions, ladies and gentlemen? Good. Make sure you bring this with you tomorrow.